Tonight, we drift toward the Boomerang Nebula, the coldest known place in the universe. A ghostly silence colder than the deep void of space itself, where even the movement of atoms slows to a gentle pause. Welcome to the Orbit for Sleep channel. Here, science moves slowly, quietly, and without urgency. Let us follow the orbit of science and drift gently toward sleep. You drift into a region of space that feels quieter than silence itself. Stars still exist in the distance, but here, motion is slow and subdued. This is the Boomerang Nebula, a small and unusual cloud of gas located in the Milky Way. What makes it remarkable is not its size or brightness, but its temperature. This place is colder than empty space. Empty space, often imagined as perfectly cold, is not truly empty of energy. Even in the vast darkness between stars, a faint background warmth remains. This is known as the cosmic microwave background, a weak afterglow left from the early universe, measured at about -270 degrees Celsius. The Boomerang Nebula is colder still, reaching approximately -272 degrees Celsius, only 1 degree above absolute zero. At this temperature, heat energy is almost entirely absent. On Earth, extreme cold might mean ice, frozen air, or brittle metal. In everyday life, a freezer operates around -18 degrees Celsius. Even the coldest places on Earth never come close to this. The Boomerang Nebula exists in a state far beyond any natural cold humans experience. This extreme cold does not come from distance or darkness alone. At the center of the nebula is a dying star, once similar to the Sun. In a late stage of its life, the star began shedding its outer layers at very high speed. Gas rushed outward faster than 150 kilometers per second. As the gas expanded, it cooled rapidly through a process called adiabatic cooling. This is the same effect felt when air escapes quickly from a spray can and the metal becomes cold to the touch. In the Boomerang Nebula, this effect occurs on a stellar scale. The gas expands so quickly that it loses internal energy faster than surrounding space can supply it. The result is a region colder than the background of the universe itself. The nebula briefly becomes a pocket where temperature drops below the natural cosmic minimum. Astronomers identified this phenomenon in the late 20th century by observing how the gas absorbed specific wavelengths of light. These absorption patterns revealed both motion and temperature, allowing scientists to confirm that this nebula holds the coldest known environment ever observed. The Boomerang Nebula demonstrates that the universe is not defined only by extremes of heat and violence. Under certain conditions, expansion and motion can create profound cold. This cold is temporary, lasting only as long as the gas continues to expand. Over time, the nebula will warm and fade, blending back into the surrounding galaxy. Here, colder than empty space, the universe reveals that even near absolute zero, change continues quietly, governed by simple physical rules acting on an immense scale. You remain within the quiet boundaries of the Boomerang Nebula, where motion feels restrained and energy scarce. The cold here is not accidental. It is the direct result of very specific physical conditions that make this nebula the coldest known object in the universe. The key factor is speed. At the center of the nebula lies a star nearing the end of its life. Unlike stars that explode violently, this star releases its outer atmosphere in a steady but extremely rapid outflow. Gas is expelled outward at speeds exceeding 150 kilometers per second. This velocity is unusually high for a dying star and sets the Boomerang Nebula apart from typical planetary nebulae. As the gas streams away from the star, it expands into surrounding space. Expansion causes cooling because the gas must use its internal energy to push outward. This process is known as adiabatic cooling, a term that simply means cooling without adding or removing heat from the outside. A familiar version of this happens when air is released from a tire or aerosol can. Escaping air cools instantly, even though the surrounding environment remains unchanged. In the Boomerang Nebula, this effect is amplified by scale. The volume involved is vast, and the expansion is continuous. The gas cools faster than it can absorb heat from nearby radiation or from the faint warmth of space itself. As a result, the temperature drops below the cosmic microwave background, the residual heat left from the early universe. This is a rare condition. Most objects in space cannot become colder than the background radiation that fills the universe. The Boomerang Nebula bypasses this limit briefly by isolating its gas from external heat sources while maintaining extreme expansion speed. The nebula essentially creates its own cold environment, detached from the thermal balance of surrounding space. Astronomers confirm this by studying how the gas interacts with light. Molecules within the nebula absorb specific radio wavelengths in a way that only occurs at extremely low temperatures. These observations, made in the late 20th century, allowed scientists to calculate the nebula's temperature with confidence. What makes the Boomerang Nebula the coldest known object is not distance, shadow, or age. It is motion. Rapid expansion transforms energy into structure, and structure into silence. For a brief moment in cosmic time, the physics of motion overcomes the ambient warmth of the universe, producing a region colder than empty space itself. Within the Boomerang Nebula, temperature approaches a boundary that physics itself defines. The value often cited, -272 degrees Celsius, is not simply an impressive number. It represents a state extremely close to absolute zero, the theoretical limit where all classical motion of particles nearly stops. Temperature is a measure of motion. In everyday life, warmth comes from movement at the microscopic level. Air molecules bounce faster in a warm room and slower in a cold one. When a cup of coffee cools on a table, the motion of its molecules gradually slows as energy spreads into the surrounding air. Cold is not a substance, but the absence of motion. Absolute zero lies at -273 degrees Celsius. At this point, particles retain only minimal quantum motion that cannot be removed. No natural environment can reach or cross this limit. The Boomerang Nebula, at -272 degrees Celsius, comes within 1 degree of this boundary. In cosmic terms, this difference is extraordinarily small. To understand how extreme this is, it helps to compare it with familiar temperatures. The coldest winter nights on Earth reach around -90 degrees Celsius in polar regions. Liquid nitrogen, commonly used in laboratories and medicine, boils at -196 degrees Celsius. Even these extremes leave a vast gap between human experience and the conditions inside the nebula. At -272 degrees Celsius, gas behaves very differently. Atoms move so slowly that collisions become rare. Energy exchange nearly halts. Radiation emitted from the gas becomes extremely faint. The nebula does not glow strongly or shine with color. Instead, it absorbs radiation from behind it, appearing as a cold silhouette against the background of space. This temperature also explains why the Boomerang Nebula is temporary. Such extreme cold can only be maintained while the gas continues expanding rapidly. As expansion slows, even the faint warmth of surrounding space will begin to raise the temperature. The nebula will gradually lose its record-breaking status and blend back into the thermal balance of the galaxy. Minus 272 degrees Celsius is not just a measurement. It marks the edge of what temperature can mean in the universe. In the Boomerang Nebula, motion nearly disappears, energy rests, and the laws of physics reveal their quietest possible state without ever reaching complete stillness. You observe the Boomerang Nebula without seeing it glow. Its cold is not revealed through brightness, but through absence. Astronomers did not discover its extreme temperature by measuring heat directly. Instead, they learned to read how cold matter interacts with light. In space science, temperature is often inferred rather than touched. Gas clouds announce their conditions through the way atoms and molecules absorb and emit radiation. In the case of the Boomerang Nebula, scientists focused on radio wavelengths, a region of light well suited for studying cold material. The key clue came from absorption lines. When radiation from background stars passes through the nebula, certain wavelengths are absorbed by molecules inside the gas. These missing frequencies appear as dark lines in radio spectra. Their depth and shape depend on temperature, density, and motion. Astronomers noticed that the Boomerang Nebula absorbed more radiation than expected, even compared to empty space. This indicated that the gas was colder than the cosmic microwave background. Such a result is rare because most interstellar clouds emit energy rather than absorb it. Motion also played a role in the measurement. The absorption lines were shifted due to the rapid expansion of the gas. By analyzing this shift, scientists determined the speed at which the nebula was growing. High expansion speed combined with strong absorption pointed directly to adiabatic cooling on an extreme scale. This method resembles how weather is inferred on Earth from a distance. A satellite does not feel temperature directly. It reads patterns in infrared and microwave signals to calculate heat, wind, and pressure. In a similar way, astronomers reconstructed the physical state of the Boomerang Nebula using indirect but reliable signals. These observations were made in the late 20th century using radio telescopes capable of precise spectral measurements. The consistency of the data across different instruments confirmed that the nebula's temperature truly fell below the background radiation of the universe. Through absorption rather than emission, through missing light rather than brightness, the Boomerang Nebula revealed its secret. The coldest place known in the universe was identified not by what it showed, but by what it quietly removed from the light passing through it. You shift attention from temperature to structure and notice that the Boomerang Nebula is not a uniform cloud. Its extreme cold is contained within a rapidly expanding shell of gas that surrounds the central star like a moving boundary. This shell formed as the star began to lose its outer atmosphere. Instead of drifting away slowly, the gas was expelled outward in a concentrated flow. Over time, this outflow created a thick envelope that continues to move away from the star at remarkable speed. The shell is not solid, but its density is high enough to shape how energy moves through the nebula. As the shell expands, its volume increases faster than its ability to retain heat. Energy is spread thinly across a growing space, leading to strong cooling. The outer layers become colder than the inner regions, forming a gradient where temperature decreases with distance from the star. This layered structure helps trap the coldest gas inside the expanding envelope. In everyday terms, this resembles the way cold air behaves when released quickly from a compressed container. The air closest to the opening cools first and most strongly, while regions farther away adjust more slowly. In the Boomerang Nebula, this simple physical behavior unfolds across trillions of kilometers. The shell also plays a protective role. Its density blocks external radiation that would otherwise warm the interior. Starlight from the galaxy, infrared emission from dust, and the faint background radiation of the universe are partially absorbed or scattered before reaching the coldest regions. This shielding allows the nebula to maintain temperatures below the cosmic background for a limited time. Observations show that the shell is not perfectly smooth. Variations in density and speed create subtle structure within the gas, hinting at changes in the star's mass loss over time. These patterns act as a record of the final stages of stellar evolution, preserved in motion rather than light. The rapidly expanding gas shell is therefore not just a consequence of the nebula's formation. It is the mechanism that creates, maintains, and defines the coldest natural environment yet observed. Structure and motion work together here, turning expansion itself into a tool for extreme cooling. You focus on the process that governs everything inside the Boomerang Nebula. The extreme cold does not come from an external freezer or a shadowed corner of space. It emerges from a simple physical rule applied on an enormous scale, known as adiabatic cooling. Adiabatic cooling occurs when a gas expands without gaining heat from its surroundings. As the gas spreads outward, it must spend its internal energy to do work against pressure. That energy loss appears as a drop in temperature. No heat is removed from the outside. Cooling happens purely through motion. A familiar example appears in everyday life. When air escapes quickly from a spray can, the metal surface becomes cold. The gas inside expands rapidly, losing energy as it pushes outward. The surrounding room does not change temperature, yet the escaping gas cools dramatically. The same physics operates in the Boomerang Nebula, but on a scale measured in trillions of kilometers. Near the central star, gas is expelled at exceptional speed. As it rushes outward, the pressure drops sharply. The particles spread farther apart, collide less often, and carry less kinetic energy. Temperature falls not because the nebula is far from stars, but because expansion outpaces energy replacement. In most cosmic environments, adiabatic cooling is limited. Expansion slows, or incoming radiation reheats the gas. In the Boomerang Nebula, both limits are briefly avoided. The outflow remains fast, and the surrounding gas shell shields the interior from external warmth. This allows adiabatic cooling to continue far beyond typical cosmic conditions. This process explains why the nebula can become colder than empty space. The cosmic microwave background sets a thermal floor for most objects, but adiabatic expansion temporarily drives the internal temperature below that level. The gas is not isolated forever, only long enough for physics to reach an extreme. Adiabatic cooling on a stellar scale reveals how basic rules remain unchanged regardless of size. The same principle that chills a spray can governs the coldest natural environment ever observed. In the Boomerang Nebula, expansion itself becomes the engine of silence, slowing motion until temperature nearly disappears. At the center of the Boomerang Nebula, a single star quietly shapes everything around it. This star is not exploding, and it is not yet a white dwarf. It is in a brief transitional phase, steadily losing its atmosphere as it approaches the final stages of stellar evolution. Stars like this spend most of their lives balancing gravity and pressure. Energy produced in the core pushes outward, while gravity pulls inward. For billions of years, this balance holds. Eventually, as nuclear fuel becomes harder to sustain, the balance weakens. The outer layers are no longer held as tightly and begin to drift away. In the Boomerang Nebula, this mass loss is unusually intense. The star sheds its atmosphere not as a gentle breeze, but as a fast, concentrated outflow. Large amounts of gas are released in a relatively short time, forming the expanding shell that defines the nebula. This behavior suggests a brief but unstable phase in the star's life, possibly influenced by changes in internal structure or unseen companions. On Earth, a similar idea appears when pressure is suddenly released from a sealed container. The contents escape rapidly once confinement weakens. In the star, gravity plays the role of containment. As that grip loosens, material escapes outward into space. As the atmosphere leaves the star, the exposed core grows hotter, even while the surrounding gas becomes colder. This contrast is common in stellar evolution. Energy concentrates inward as matter flows outward. The Boomerang Nebula captures this moment in motion, freezing a transition that usually passes quickly. Astronomers study this stage because it determines how stars return material to the galaxy. The gas lost from aging stars becomes part of future clouds, planets, and stars. In this case, the material is marked by extreme conditions that reveal how mass loss can reshape temperature and structure far beyond the star itself. The central star, slowly stripping itself of its atmosphere, is therefore not separate from the nebula's cold. Its quiet transformation is the source of the expansion, the structure, and the brief creation of the coldest natural environment yet observed. You follow the motion of the gas as it moves outward, and notice that expansion itself is the source of the extreme cold. In the Boomerang Nebula, cooling is not caused by contact with something colder. It is produced by the simple act of spreading out. When gas expands, its particles move farther apart. To do this, they must use energy. That energy comes from their own motion. As particles lose kinetic energy, their speed decreases and temperature falls. This relationship between motion and temperature holds everywhere, from everyday air to interstellar space. A familiar example appears when a bicycle tire is deflated. As air rushes out, the escaping gas cools immediately. The rubber valve may feel cold to the touch, even though the surrounding air remains unchanged. No external cooling is involved. The temperature drops because energy is spent on expansion. In the Boomerang Nebula, this process is pushed to an extreme. The gas is released rapidly and continuously, not in a brief burst. Expansion happens faster than radiation from stars, or the background of the universe can replace the lost energy. Each second of outward motion deepens the cooling effect. Pressure plays a central role. Near the star, gas is dense and compressed. As it moves outward, pressure drops sharply. Lower pressure allows particles to separate further, reducing collisions and slowing motion. Fewer collisions mean less internal energy is shared, reinforcing the temperature decline. Most cosmic clouds do not reach such low temperatures because expansion eventually slows. Gravity, surrounding material, or incoming radiation restores balance. In the Boomerang Nebula, expansion remains dominant long enough to overpower these stabilizing effects. Extreme cold, in this context, is not a property of space itself. It is a consequence of motion that outruns equilibrium. The Boomerang Nebula shows that spreading matter thinly and quickly can drain energy more effectively than distance or darkness alone. Expansion becomes a natural engine for cold, shaping one of the quietest environments the universe can briefly sustain. You notice that the Boomerang Nebula is not round or evenly spread. Its structure narrows at the center and widens outward, forming a shape that resembles a curved blade or a bent arc. This distinctive form is not decorative. It is a record of motion, direction, and constraint. The shape emerges from how the gas leaves the central star. Instead of expanding equally in all directions, the outflow is focused along two opposing paths. These bipolar flows channel material away from the star more strongly along a preferred axis. Over time, this creates two lobes extending outward, giving the nebula its characteristic appearance. Rotation plays an important role. As the star loses mass, any existing spin influences how material escapes. Gas moving along the equatorial region encounters resistance, while gas aligned with the rotational axis can travel more freely. The result is a pinched center and elongated extensions. A similar effect can be seen in everyday situations. When water sprays from a rotating garden sprinkler, the flow does not form a perfect sphere. Direction, spin, and pressure shape the stream into distinct patterns. In space, the same principles apply, though the scale is vastly larger and the timescales far longer. The surrounding gas shell also contributes to the shape. As expansion continues, faster-moving regions stretch farther outward, while slower regions lag behind. Small differences in speed become large differences in distance. The nebula's outline becomes sharper as motion separates material into layers. Astronomers interpret this shape as evidence of structure rather than chaos. It suggests that the star's mass loss followed an organized pattern, possibly influenced by magnetic fields or an unseen companion star. These influences guide the flow without requiring explosive forces. The Boomerang Nebula's shape is therefore not incidental. It is the visible imprint of direction, rotation, and time. The coldest place known in the universe also carries a clear geometry, showing that even in extreme conditions, physical laws leave orderly signatures behind. You shift perspective from the vastness of space back toward familiar ground. To understand the cold of the Boomerang Nebula, it helps to place it alongside the coldest environments humans know on Earth. On our planet, the lowest natural temperatures occur in Antarctica. In the early 21st century, satellite measurements recorded surface temperatures near -90 degrees Celsius on the Antarctic plateau. Even in these conditions, air still moves, ice still forms crystals, and physical processes continue at a pace humans can observe. Compared to this, the Boomerang Nebula exists in an entirely different thermal category. At -272 degrees Celsius, it is more than 180 degrees colder than Earth's coldest recorded environments. This difference is not incremental. It represents a near-total removal of thermal motion. On Earth, extreme cold affects materials in visible ways. Metals become brittle, rubber stiffens, engines fail because lubricants thicken and stop flow. Yet atoms and molecules still vibrate enough to transfer heat. In the Boomerang Nebula, that vibration is reduced to a minimum set by physics itself. Human-made environments can approach lower temperatures, but only briefly and with effort. Cryogenic laboratories use liquid helium to reach temperatures just a few degrees above absolute zero. These conditions require insulation, vacuum chambers, and continuous energy input. Nature rarely produces such isolation on its own. The comparison highlights an important difference. Earth's cold is shaped by weather, sunlight, and atmosphere. The nebula's cold is shaped by motion and expansion. One depends on environmental balance, the other on a rapid escape from balance. By placing the Boomerang Nebula alongside Earth's coldest places, scale becomes clearer. The nebula is not simply colder than anything humans experience. It occupies a region of temperature that lies beyond natural terrestrial limits, showing how the universe can reach extremes that planets with atmospheres never can. You bring the scale even closer to human hands, where extreme cold is produced deliberately, briefly, and with great effort. In laboratories on Earth, scientists have learned how to approach temperatures near absolute zero, but only under carefully controlled and artificial conditions. These environments represent the furthest reach of human technology, designed to slow matter almost to a standstill. Ultra-cold experiments rely on isolation above all else. Atoms are trapped inside vacuum chambers where air has been almost completely removed, eliminating one of the most common paths for heat transfer. Lasers tuned to very specific frequencies are used to slow atomic motion. Each photon interaction reduces speed incrementally, cooling the atoms step by step. Magnetic fields then confine these atoms in space, preventing them from touching warmer surfaces that would immediately raise their temperature. Every layer of control exists to block heat from entering the system. One widely used benchmark in these experiments is liquid helium, which boils near -269 degrees Celsius. This substance allows scientists to reach temperatures far below those achievable with conventional refrigeration. Using more advanced techniques, such as laser cooling and magnetic trapping, researchers can push temperatures even closer to absolute zero. At these extremes, matter begins to display quantum behavior that cannot be observed at higher temperatures. Atoms act collectively, and familiar distinctions between particles blur. Maintaining these conditions is demanding. Energy must be supplied continuously to sustain the cold. Pumps preserve the vacuum. Lasers remain precisely aligned. Power systems run without interruption. The moment this control falters, heat flows back in, and temperature rises quickly. The cold exists only as long as effort is applied. The contrast with the Boomerang Nebula is clear. In space, no such maintenance exists. There are no walls, no sealed chambers, and no energy input dedicated to cooling. The nebula relies entirely on natural motion. Rapid expansion removes energy from the gas faster than it can be replaced. Scale replaces insulation. Motion replaces machinery. Everyday experience helps clarify this difference. A refrigerator cools food by actively moving heat outward using electricity. When the power is turned off, the interior slowly warms to match the room. Laboratory cooling works the same way. The Boomerang Nebula behaves differently. It resembles a container that is constantly opening, allowing its contents to spread so rapidly that temperature falls without assistance. Laboratory ultra-cold experiments demonstrate what physics allows under strict control and intention. The Boomerang Nebula demonstrates what physics can produce naturally when conditions briefly align. Both approach the same thermal boundary, near absolute zero, but one depends on precision, energy, and maintenance, while the other depends on timing, expansion, and the vast openness of space. You move from human technology to the conditions required for life itself. Temperature is one of the most fundamental limits for biological systems, and in the Boomerang Nebula, that limit is not approached, but far exceeded. This environment reveals where life, regardless of form, must come to a complete stop. Life, as it is understood on Earth, depends on motion at the molecular level. Chemical reactions require particles to collide, bond, separate, and rearrange. Proteins must fold and unfold. Membranes must remain flexible. Information stored in molecules must be copied and maintained. All of these processes rely on molecules moving with enough energy to interact. When temperature drops, molecular motion slows. As it slows further, reactions become less frequent and less reliable. Below a certain point, chemistry does not merely slow down, it effectively ceases. There is no pathway for complex systems to operate when particles rarely meet and energy cannot be transferred. At -272 degrees Celsius, the environment of the Boomerang Nebula allows almost no molecular activity. Atoms move so slowly that collisions become extremely rare. Chemical bonds cannot form or break in meaningful ways. Large molecules lose their functional shapes. Any structures associated with biology become chemically silent, locked in place by the absence of motion. On Earth, even the coldest surviving organisms avoid this state by maintaining internal motion. Cells consume energy to prevent complete freezing. Enzymes act as molecular tools that lower the energy required for reactions, allowing chemistry to proceed in cold environments. Polar bacteria, deep-sea organisms, and extremophiles operate near the lower edge of biological tolerance, but they still depend on liquid water, flexible structures, and continuous energy input. In the Boomerang Nebula, these supports do not exist. There is no liquid water, no solid surface for chemistry to organize around, and no steady energy source to sustain internal motion. Radiation is scarce. Matter is diffuse. Even if complex organic molecules were present, they would remain inert, unable to react, replicate, or evolve. This limitation is not unique to Earth-based life. Any form of life built on chemistry faces the same constraint. Without motion, information cannot be processed. Structures cannot be repaired. Change cannot occur. Temperature therefore acts as a universal boundary, defining where life is physically possible and where it is not. The Boomerang Nebula illustrates this boundary with clarity. It is not hostile, violent, or destructive in an active sense. It is simply inactive. In this near absolute cold, the processes that define life fade quietly. What remains is a region governed entirely by physics, where motion is reduced to its smallest possible measure and biology has no space to begin. You turn from physical limits to human perception. Absolute cold is not something the human body can truly sense. What people experience as cold is not temperature itself, but the rate at which heat leaves the body. Human skin contains receptors that respond to heat flow. When warmth escapes quickly, the brain interprets this as cold. Metal feels colder than wood at the same temperature because it draws heat away faster. Snow can feel warmer than air on a windless day because heat loss slows. Perception follows energy transfer, not numerical temperature. This distinction becomes important at extreme limits. As environments approach very low temperatures, sensory accuracy breaks down. Nerve signals slow, tissue stiffens. Pain and numbness overlap. Long before absolute cold is reached, perception fades and fails. The body cannot report conditions that it cannot survive. On Earth, even in polar regions, perception still operates within a narrow range. Wind chill increases heat loss, making air feel colder without changing its temperature. Protective clothing works by trapping air, reducing heat transfer rather than altering the environment itself. These strategies manage perception, not physics. In the Boomerang Nebula, perception has no role. There is no surface to touch, no medium to conduct heat, and no reference frame for sensation. Temperature there describes particle motion, not experience. Minus 272 degrees Celsius does not feel cold. It represents near absence of motion. This gap between perception and reality appears in many areas of science. Soundless space still carries pressure waves. Darkness can contain intense radiation. In the same way, extreme cold exists without sensation. Numbers replace feeling. Understanding this difference matters. Human intuition evolved in a narrow thermal window. Beyond it, physical laws continue unchanged, while perception falls silent. The Boomerang Nebula exists entirely in that silent regime, where cold is measured, not felt, and where human senses no longer apply. You step back from sensation and comparison and focus on what the Boomerang Nebula reveals about heat and energy themselves. Here, familiar assumptions give way to clearer definitions. Heat is not a substance stored inside objects. It is energy in transit, moving from regions of higher motion to regions of lower motion. Temperature measures how active particles are, not how much heat an object contains. In everyday life, these ideas blur together because conditions remain close to human comfort. The Boomerang Nebula separates them. Its gas contains matter, yet almost no thermal motion. Energy has not vanished, it has been converted. As the gas expanded, internal energy was spent doing work, pushing matter outward. What remains is structure without warmth. This distinction appears in simple experiences. When a room cools overnight, heat has not been destroyed, it has flowed elsewhere. When a compressed gas expands, temperature drops, even though no cold source is added. The nebula follows the same rule, scaled up beyond intuition. The environment also shows that cold is not a default state of space. Space contains radiation, particles, and energy fields. Most regions settle near the cosmic background temperature. Only specific processes, like rapid expansion combined with isolation, can drive temperatures lower. Energy balance governs everything. When energy enters a system faster than it leaves, temperature rises. When energy leaves faster than it enters, temperature falls. In the Boomerang Nebula, expansion ensures a continuous imbalance. Energy exits as motion and geometry, not as heat. This lesson extends beyond this single object. Stars shine because energy flows outward. Planets cool because energy escapes. Galaxies evolve as energy redistributes over time. The nebula compresses these ideas into a quiet example, stripped of light and violence. What the Boomerang Nebula teaches about heat and energy is simple and precise. Temperature follows motion, cold follows expansion, and even at the coldest natural limit yet observed, the universe remains governed by ordinary rules, applied without exception across an extraordinary scale. You extend the view forward in time and outward in scale toward the question of whether the universe might produce something colder than the Boomerang Nebula. The answer depends less on discovery and more on physics. Temperature has a natural lower bound. Absolute zero marks the point where classical motion can no longer decrease. No natural process can cross this limit. The Boomerang Nebula approaches it closely, not by removing heat, but by converting internal energy into expansion. Any colder environment would need to push this same mechanism even further. In principle, colder regions could exist briefly. A faster expansion, stronger isolation from radiation, or a more massive outflow could drive temperatures slightly lower. Such conditions would require a rare alignment of stellar mass loss, geometry, and timing. Even then, the gain would be marginal, measured in fractions of a degree. Most of the universe cannot achieve this. Interstellar clouds absorb background radiation. Galaxies are filled with starlight. Even deep voids contain residual energy from the early universe. These sources set a practical floor that prevents temperatures from falling far below the cosmic background. Human technology can approach absolute zero more closely than any known natural object, but only in small, controlled systems. Laboratories use isolation and continuous energy input to maintain these states. Nature lacks the intention and precision to sustain such conditions over large volumes. Future telescopes may discover objects that rival the Boomerang Nebula. Improved sensitivity could reveal colder gas in transient phases of stellar evolution. However, physics limits how much colder such objects could be and how long they could remain that way. The significance of this question lies not in breaking a record. It lies in understanding boundaries. The Boomerang Nebula sits near a physical edge where familiar processes reach their limit. Whether or not something colder is found, the lesson remains the same. The universe allows extremes, but only briefly, and only when simple rules align in rare ways. You place the Boomerang Nebula within the long life of a star, where extreme cold appears not as an endpoint, but as a brief transition. Stars evolve slowly, spending most of their existence in stable balance before passing through short, defining phases. For the majority of its life, a star like the one at the center of the Boomerang Nebula burns fuel steadily in its core. Gravity pulls inward, while pressure from nuclear reactions pushes outward. This equilibrium can last for billions of years. Temperature and structure change gradually, almost imperceptibly. As fuel becomes harder to sustain, the balance weakens. The star expands, sheds mass, and enters a late evolutionary stage. Material once held tightly begins to escape. In most cases, this loss is moderate and produces a warm, glowing planetary nebula. In the Boomerang Nebula, the mass loss is unusually fast, creating conditions for rapid expansion and extreme cooling. This cold phase is short-lived. As the gas continues to spread, density falls and external radiation begins to penetrate. The temperature rises toward the cosmic background. Meanwhile, the central star contracts and heats up, moving toward its final state as a white dwarf. Everyday experience offers a parallel. When a balloon is released suddenly, the escaping air cools briefly, but the effect disappears as the system stabilizes. The Boomerang Nebula captures a similar moment, stretched across space and time, but governed by the same physics. Seen this way, the nebula is not an anomaly detached from stellar evolution. It is a snapshot of a narrow window between stability and collapse. Most stars pass through this window too quickly, or under less extreme conditions, to leave such a cold imprint. Within the life cycle of stars, the Boomerang Nebula represents a transient chapter. It shows that even near the end of stellar life, ordinary processes can combine to create extraordinary extremes before returning quietly to the broader flow of cosmic evolution. You consider cold not as a permanent feature of the universe, but as a temporary condition shaped by motion and time. In cosmic terms, extreme cold is rarely stable. It appears, evolves, and fades as systems move toward balance. Temperature reflects how energy is distributed. When that distribution is uneven, change follows. Regions that cool rapidly tend to warm again as energy flows in from their surroundings. The universe constantly works toward equilibrium, smoothing out extremes whenever possible. The Boomerang Nebula illustrates this process clearly. Its extreme cold exists only while expansion remains rapid and shielding remains effective. As the gas spreads outward, density decreases. External radiation penetrates more easily. The temperature slowly rises toward the background level of the universe. This behavior is common across cosmic environments. Shock waves cool as they expand, then warm as surrounding energy catches up. Interstellar clouds collapse in heat, then radiate and cool. Galaxies experience bursts of activity, followed by long periods of quiet adjustment. Extremes rarely persist. Everyday experience reflects the same pattern. Ice removed from a freezer does not stay cold indefinitely. It warms as energy from the room flows inward. A breath on a winter day briefly condenses into fog, then disappears as it mixes with surrounding air. Temporary imbalance produces visible change, then fades. Even the coldest known regions follow this rule. Without continuous expansion or isolation, temperature drifts back toward average conditions. Stability favors moderation rather than extremes. Cold, in this sense, is not a destination. It is a phase. The Boomerang Nebula marks a moment when energy distribution is unusually skewed. Given time, that imbalance dissolves, leaving behind only the quiet trace of a transition that briefly pushed the universe to its coldest edge. You examine temperature not as a local condition, but as a quantity bounded by universal rules. The universe allows a wide range of temperatures, yet those extremes are constrained by fundamental limits that cannot be crossed. At the lower end lies absolute zero, the point where classical thermal motion reaches its minimum. No natural process can reduce temperature below this boundary. Even at absolute zero, particles retain a small amount of quantum motion, ensuring that complete stillness never occurs. Most regions of the universe never approach this limit. Radiation left over from the early universe fills space with a persistent background warmth. Starlight, dust emission, and particle interactions continually add energy to cosmic environments. These influences establish a practical lower bound that keeps temperatures from falling freely. Reaching temperatures below this background requires special circumstances. Energy must leave a system faster than it enters. Expansion, isolation, and timing must align precisely. Without these factors, thermal balance quickly reasserts itself. At the upper end of the scale, temperature is also limited. As matter becomes hotter, particles move faster, and collisions become more energetic. Beyond certain thresholds, atoms break apart, nuclei dissolve, and matter transforms into plasma. Even here, physical laws govern how energy is stored and released. Everyday experience reflects these constraints in simpler form. Water freezes at a fixed point and boils at another under normal conditions. Pressure can shift these points, but the transitions remain defined. The universe follows similar principles, though applied across immense ranges of energy and scale. The Boomerang Nebula occupies a position near the lower boundary of this spectrum. It does not violate physical laws. It demonstrates how close those laws can be approached when conditions briefly allow it. Temperature limits in the universe are therefore not arbitrary. They are expressions of deeper rules about motion, energy, and equilibrium. The extremes we observe are signposts, marking where familiar behavior gives way to fundamental structure and where nature quietly enforces its boundaries. You arrive at the quiet conclusion of the journey, where extreme cold becomes a tool for understanding rather than a curiosity to surpass. The Boomerang Nebula does not matter because it is the coldest place known. It matters because it clarifies how the universe works when pushed to its limits. Extreme conditions strip systems down to their essentials. In the Boomerang Nebula, light is faint, chemistry is inactive, and motion is minimal. What remains are basic physical rules acting without distraction. Expansion reduces energy. Isolation slows change. Temperature follows motion. These relationships become easier to see when complexity falls away. This is why extreme cold is valuable to science. Near absolute zero, familiar processes pause, allowing hidden structure to emerge. In laboratories, cooling matter reveals quantum behavior. In space, cooling gas exposes how energy flows across vast distances. The principles are the same, even when the scales differ by trillions. The nebula also reminds us that extremes are informative because they are rare. Most of the universe operates far from its limits. Stars shine, planets orbit, and galaxies evolve under moderate conditions. By contrast, the Boomerang Nebula represents a moment when balance briefly breaks, creating clarity through simplicity. Everyday experience reflects this idea in smaller ways. A slowed-down recording reveals details missed at full speed. A quiet room makes subtle sounds noticeable. When motion decreases, patterns become easier to trace. Extreme cold performs the same function for the universe, slowing activity, so underlying rules stand out. Understanding the universe does not require dramatizing its dangers or exaggerating its mysteries. It requires observing where rules become visible. The Boomerang Nebula offers such a place. By approaching the coldest edge allowed by physics, it turns temperature into a lens, helping us see how energy, motion, and structure quietly govern everything around us.